Good afternoon. Slides is visible.
Yes, sir.
Okay.
Excuse me, sir.
Yes, please.
So, just a question. Would you be sharing the slides?
Yeah, I'm sharing the slide. Okay. I'm
Okay.
working on this because there is something we have to done. Then just share.
No, sir,
Just
just
write it
wanted to know.
within the part. Yeah.
Thank you, sir.
Okay. So we were discussing the method algorithm to find the local optima or the kind of basically minimum of this cost function. And so what we said that the function is basically j theta theta 0 theta 1, and that function actually we have said that this function is this look like this. As you see, this is the function. So we have to write it. So this j theta 0 theta 1 is basically the function that is h theta of yi minus the actual yi. You can say that yi hat something, and this we take a square root and it sum it up with I is equal to 1 to total number of sample, where m is equal to number of training sample, number of number of training sample, and then this normalization comes this. So this is basically your g of theta 0 theta 1, and these things we have to minimize. Okay, so we're trying to minimize this function theta 0 and theta 1. Okay, I think this is yeah, that is the thing, is that of j of theta 0 theta 1.
Sir, it
Okay,
should h theta of xi, I think.
yeah, that is actually. Thank you for this. It is theta xi, so xi is the point, that is fine. And its corresponding y is actual point. So this is the thing we have to. So we have to minimize this, and we start with now what we'll do. We start with, as I said, we start with a arbitrary theta, and then we see here we can start with arbitrary theta, theta 0 theta 1, and let's keep on changing this theta 0 theta 1, so we get the to find this particular local minima or kind of minima, can say. So here that we have discussed that if we start with this, we can, maybe we are basically starting to for the different, these are the different points, theta 0 theta 1 points. This we're starting point is this initial theta 0, and this way we are converging to the kind of local optima kind of thing. So these are the path. And if we start with a different position, maybe we end up with a different minimum position. Since this is not a convex in nature, we can have multiple local optima, so that we can just go and end this in this point in this way. So this is the gradient descent. So if we say that algorithm is that we do a loop that is called repeat until convergence. Okay, so that convergence is basically this. There is a prescribed error threshold. If the threshold is less than this, we can stop. So basically what we're going to do, that this theta, how actually theta is being changing. So theta j means that by a particular instant, that is theta j minus, I'm coming how actually we get this, but this is a kind of parameter alpha, and d of d theta j. Okay, and this is basically we can take the derivative of this j of theta 0 theta 1. Please unmute, sorry, please mute all these mics because there is some noise is coming. Okay, now this is theta j, and theta j is equal to 1 to j0 and j1. We can do this particular equation. And now one thing is important. What is alpha? This alpha. This alpha is called the learning rate. Please mute yourself. Okay. Now we'll show later also that how geometrically this alpha will going to affect this algorithm. But here it is that the main implication of alpha, that it controls how bigger steps we are taking over the gradient descent. So if you see that if it is a take a, you can see in the next blue slide, if you this is a single dimensional error surface. This is two dimensional because j theta 0 theta 1, but if just for example this is j theta, that is the same univariate in just hypothetically very. So now the thing is that this alpha is something like that. If it is a small, then these steps are very tiny, kind of this kind of steps is there. Okay, so this in this way. And if it is a high, then maybe it's from here to straight away it come here, and then it come, then straight away it can here, or it can here, this can kind of thing will happen if it is a big. So that is the thing that we will see this picture, this kind of graph later also. So that this, it controls how bigger steps we will taking over the gradient, is the gradient constant. So what is the step? So we can take two temporary variable, temp 0 and temp 1. And temp 0 is basically theta 0 minus this learning rate into d of the theta 0 of j of theta 0 theta 1. And theta 1 is basically alpha of this theta 0 theta 1. And then we change theta 0 theta 1 to the temp 0 and temp 1. Now you can see, don't look that the temp 0 and theta 0 temp 0, because this theta 0 is again used here, so it's a correct, is the incorrect step. So this is the correct order of changing the theta 0 theta 1. Okay, so this is where this is the just algorithmic, or you can say the algorithmic steps to find the for this gradient algorithm. Okay, so now we try to find out that how it makes sense, why this kind of thing is basically some sort of mathematical implications of this algorithm. Let it single variable. So now that is for initially we can say this error surface is basically a plane. Okay, so it's a two-dimensional. Now I will say, for sake of your understanding, that this j of theta or theta 1 whatever, that is a single dimensional error surface. So we have to minimize this, minimize theta 1 j of theta, where theta is equal to beta r. So this gradient descent algorithm is now what? Theta is equal to theta minus alpha of d theta 1 on of j of theta 1. So that is just this most simple form kind of thing. So that is what is been written here. Okay, now see what is happening. Now how we can say that this kind of mathematical formulation will really works? That is some sort of kind of geometrical you can say proof. kind of thing. Now you see this equation I've written here. Now this, what is this? This is basically a slope because it's a derivative term. Now if it is a slope, then you can see that you here this j of theta 1. Now if you are here, let you are here because the value of theta 1 is here. So theta 1 is here, so you are here. So now the question is that this particular thing, if you, if what is the geometrical interpretation of that? If you write a tangent in this point, so in this, if you write a tangent in this point, this is the basically the your, let's say, angle with this axis. Okay, so if it is the axis, because this is a theta 1 axis, now this axis is positive, you can say, so slope is positive. So this is positive, so this particular slope is greater than 0. So now the problem is that now you are in here, basically in theta 1 axis you are here. Now theta 1, if your theta 1 is there and positive is slow and alpha is again a positive number, now what is happening? So theta is here, theta 1 is reducing, because now actually local minimum here, so this theta 1 is definitely higher than this local minima, so you have a basically theta 1 is reduced and it is going towards this direction. So the convergence is in the proper direction. So convergence means what? Convergence means that you can reach here. So that is means convergence, or very close to that. That means a convergence. So theta was is reducing. So this equation makes sense. Now, if you say, if you are here, now here you can say that this particular line, now if you take the tangent over that, this tangent is here, but this is a kind of negative angle. So because this slope is negative. Okay, so now if this is the case, now this fellow is negative, this is positive, so theta 1 minus, so minus something, so it essentially it become plus. So because you are here, so you are here, so then theta 1 has to be increased to reach the local minima here. So that is basically, it is increasing. So this theta was an increase. Previously it was decreased, now it is increased, if it is there. So it is coming to here, to the local, and here also it is coming to here, to the local minima. So this is the illustration of that, or geometrical illustration, so that this particular equation makes sense. Okay, and you can easily to make it in a two-dimensional or any higher dimensional. So it is same thing, basically. Geometrically it is same thing. Now, what we have just said, that what actually happened of this, what is the implication of this alpha? So alpha is too small. So this is at a very tiny step, as it is shown it here. So if this alpha is very small, then convergence or rate of convergence is slow. ये तो ठीक ही जा रहा है, steady जा रहा है, but it is very slow. But if you make it high, make it too large, I'm not saying the optimal, but it's too large, then what happened? This will make it here. This from there it will go there, and from here what happened? It will go here. So it's just a kind of dangling kind of thing. It was just a kind of some random thing. It will happen, and it may not never converge, or it may fail to converge. So it may fail to converge. So it should not be too small. So if so alpha should not be too small. Again, not be too high.
Sir, I have a
Yes,
doubt.
please.
Sir, so alpha is the learning rate of our machine, yes?
Learning rate of not machine, learning rate of
Of
this
our
algorithm.
algorithm.
Hmm.
Yes, exactly.
Hmm.
So if our algorithm is too good to learn some training data about some training data, then it is actually bad. Like if it is too fast to learn, it is too fast in learning. So does
Why
that
it you
imply
say
that our
it is
algorithm
bad?
is actually
Why you are saying it is too bad if it is learning
so? Because
correctly?
just now you said that if alpha is too large, that means if our algorithm is too good, then we might never reach to the local minima.
I didn't say that. That alpha is learning rate. That means that how, so the rate of convergence. So alpha is basically uh, um, you can say alpha is control. It's a control. It controls the rate of convergence. It's basically control the rate of convergence. Rate of convergence. That's all. But that doesn't mean this alpha is rate of learning or rate of just rate of convergence. That doesn't mean it is high alpha means it's a good learner. I never said this, and this doesn't mean this also. This what you are thinking is wrong, because it doesn't mean that if you making a large alpha that you are getting a good algorithm. No, the value, the optimal value is important of alpha, not too high, not too small. Okay, so this is the
All right.
integration.
All right, sir. Thank you.
So now what we said that our, so what is our assumptions till now? So far what we have discussed, that we have discussed that our h theta is basically what what is our h theta is, or h, it is basically the that was theta 1 x plus theta 0. So this x is a univariate kind of thing. So it is possible that theta 0 plus theta 1x. So this is a univariate concept, the univariate hypothesis function. Now it may be possible that we get a multivariate like this x1, x2, and so on to xn. So it is possible to get a multivariate hypothesis function like this. Okay, so it is just an extension of our previous thing. Now here x is a vector, this x is a vector because it's a multivariate, and x0, x1 to up to xn. So this is n minus n plus 1 elements there, and theta is what, theta 0, theta 1 up to theta n is also n minus n plus 1. So and theta tx, so basically that means it is theta transpose x. So now our h theta of x is nothing but a theta transpose x. Now this x is a vector, this theta is also a vector, you can say in this way. So this is a some dimensional vector of a given dimension. So, and it looks like this. So this is basically the thing. So this is basically your hypothesis function where this theta and this x both are vector, and that's all. This is the multivariate case. Okay, so now we go and and understand what is the multivariate gradient descent. Okay, so here it is that our h theta is equal to theta transpose x. So it looks like theta 0 x0, theta 1 x1, theta 2 x2, and so on, theta n xn. And parameter this theta, these are n dimensional vector, the n, sorry, n plus 1 dimensional vector. Okay, so cost function is like this. So it just either this is the same thing, because only this theta, this is a, now theta is a high dimensional vector or n dimensional vector. Better to say n plus 1 dimensional vector. So other than that is something, some same thing. So now j theta is a vector kind of thing, and this is the safe cost function. Okay. Now in gradient descent, we repeat same thing. Now just that was previously it was written that j theta is equal to j theta minus alpha of d theta j of j of theta 0 theta 1. Now here this particular fellow will now become just j of theta 0 theta 1 dot theta n. So it's n dimensional vector, nothing else. So everything is become same. So just dimensionality increase, nothing more than this. Okay. Now our algorithm previously, this is this theta 0 and theta 1 for theta 0 and theta 1, we are basically do the same thing. That is the d theta of j theta is basically this for single dimensional case. The new algorithm is that is basically same. This d of d j theta is now become x of I minus y x of I. So basically that we have to do all these things, theta 0 this, for theta 1 this, for theta 2 and it is 1 for theta n. So we can do some likewise. So I am just this analytical practice is just for doing some sort of the multivariate case. Okay, so this is multivariate gradient. Okay, now there is another interesting concept that is called feature scaling. It is featured scaling is sometimes we is more popular. It's called feature normalization. And this is also in now sometimes who are basically bit familiar with deep learning or machine learning. Sometimes we call this called batch normalization, this kind of or batch. So this is somewhat related to this. What is feature scaling and why it is required? First, you have to understand what is the kind of range of features. So make sure the features in a similar scale. So similar scale means this, you just recall your size of uh, your size of your house. Now size of your, let one feature is size of the house. And this particular thing is size square feet by 2000 or something, sorry, it is size is 0 to 2000 feet. Okay, so this is the size of the house and this is x1, let it is one feature. Another feature is called number of bedrooms. So number of this is the range of this is maybe 2000 square feet. Okay, now this site is number of bedrooms and this size of the and number of bedrooms. That this range is 1 to 5. So this is a very tiny range, but it's a huge range. Now these two feature, if you do these two feature as usual, then there is some sort of imbalance in feature range. So we can normalize both feature in a same range. Let's say we're trying to do it because these features are x, xi's, or feature is xi's, is all is to 1. So this is the range of every feature. So what we can do, we can x by size of its square by 2000. So everything coming under 0 and 1. And same thing, x2 is the number of bedrooms, so maximum 5. So it is again can be 0 and 1. So now that if this, why it is going to help. Now if you see the j theta without feature normalization, this is basically a contour plot that without this feature scaling or feature normalization. Okay, then you can say the pathway, this is the path of convergence, is a bit random in nature. Okay, So this path is quite random. You can say, I mean, this in this a zigzag, where the zigzag is very high. But if you do a kind of feature scaling, then these are the contour plot is bit circle in nature and kind of thing that this way is more straightforward, relatively straighter. Should not say this. This is roughly you can say that some approximation. Approximately you can say that J some sort of bit straight. And if it is treated so that the number the complexity of this kind is bit lesser than this. So get every feature into approximately this and this range. So this thing, if time permits, we'll come up with a more explanation of this thing, because something we have to again say that this kind of how this rationalization kind of, if time permits, will definitely take a. Okay, so this is another important concept for this regression supervised setting. Okay, so these are the very primitive or is very fundamental discussion on linear regression. Then we go for say logistic regression. Okay, so what do you mean by logistic regression? First, to understand. And in the later half, you can say that we say the logistic regression as a classification. Why logistic regression is a classification, or what is the thing? Now, here you can say that in our linear regression, in a kind of problem, it is basically a problem that the continuous y value or y output value as output. So that is the major thing of linear regression. Now, if we see that we have to find some sort of a particular object, this is a problem of a object saliency. So what do we mean object saliency? That a particular object is in a is important or not, or salient or not. So you can see that objects, this x-axis in of object size, and what y-axis is basically the saliency. Okay, so this is the between these settings is there. And if you say that size is higher, then you can say this object is most predominant. Let's say there is an image and there is some size of this image, and there is a, let's say, let's say human of size this, and there is a human of size this. Okay, and what I said that this object, since its size is higher, then this object is basically more salient. So saliency wise it is more saliency or more salient. Okay, so this is the idea actually. So now the size basically. Now, if we do this kind of orientation or this kind of data distribution, so these these x's are basically the size, large size, because it is the right hand side of the x-axis, and these are the smaller size. And so what we can do, we can write a linear regression kind of thing. So this is going to be a, and if you object that in between, so you can say if we do this, that in object 0.5 this we can get a kind of separator out there. So you can see that separator is something like that, is separating these two things. So even if it's a discrete in nature, because this is to one or no discrete in nature, uh, this particular setting, even if the linear regression setting is fine. So the threshold output is something like that, 0.5. If h theta is equal to greater than 0.5, predict 1. So this portion is basically 1, and this portion is 0, kind of thing. So basically this is 0, this sorry, this is, this portion is So this is something like that. Okay, so this is the way we actually do. But it basically looks fine. There's no problem. But it just, I'll show in the next slide that this just a kind of a lucky, um, you can say lucky case. Now you see that if one x is bit higher side, so it is also possible. Now if it is a higher side, then the corresponding this our hypothesis function, or this line fit is something like that, this theta, rather than it was initial previous example, it was this. Now it is x is here, so our kind of line is something like that. And if it is so, then the separator, that was the initial separator or previous separator. Now it is the current separator. Now you see the current separator, this, even if it is a size is high, then this size becoming a size of a kind of say less salient. So there is a, some sort of misclassification happened. Based on this data distribution, or kind of the this is basically that how um, variance that is basically the variance of this data. This data is a bit high, so that's why. So linear regression for classification purpose is not always good. So that is basically, that is the reason why value not always good. So the thing is that h theta x can be either greater than 1, less than 1. So this is logistic regression is always this thing h theta x is less than 1 or greater than 0. Okay. So this is basically, but in linear regression it makes maybe greater than 1 or maybe less than 0. This is for linear regression. But it is good enough for a logistic regression to make h theta x range. Okay. So that if this is the case, what we're going to do is that we use a logistic function on this model. So initially it was h theta, that was our hypothesis function. For linear regression, this hypothesis function is that. Now we put a g on this over this hypothesis function as a logistic function, or we can say this is called sigmoid function. This g is basically called sigmoid function. So what is this? What is the definition of this? Sigmoid function is basically that h theta x is basically, let sigmoid is basically write in this way, that g of r is equal to 1 by 1 plus e to the power minus rx. Kind of thing. Theta transpose x, so that is, so this is the definition of the sigmoid. Now here you can say, in here this r replace this theta transpose x. So h theta x now become, so when we put a sigmoid on this, so 1 by 1 plus e to the power minus theta transpose x. So this is minus r, so this is minus theta transpose x. And it look like without that how this equation, this theta transpose x, this theta, this particular function has this property, because any value of theta, whatever value is this, it is maximum, it will, if it is go, it will converge to 1, and its side is converge to 0. See, it's not 0 but very close to 0. Okay, so z is equal to gz or zr, whatever, 1 by 1 into sigmoid function or logistic function, this called. So what we are changing in case of linear regression to logistic regression, everything is same. Only we put a kind of sigmoidal function or logistic function over this transpose x. Okay, and this is basically the geometrical interpretation of this. Okay, so this sometimes in neural net is called activation function or something. We'll see later. So what happened? This hypothesis representation of this, that h theta x estimated the probability that y1 on input x. So that means it said that what is the probability of what is h theta x is? H theta x is what? Is basically that going to estimate the probability of when y is equal to when the input is x. What is the probability of y is equal to 1? That means what is the probability probability what that y is equal to 1 means something you can say the fruit is apple, given fruit is apple, you can say this y is equal to 1, or it is the object is salient, whatever is your thing, that is y. What is the probability that y is equal to 1 or something like that if x is given, or input, or if input is x. Okay, so that is the basically. So example, if x theta 0 theta 1 is object size, h theta x 0.7, that there is a 70% probability or chance that the object is salient. Okay, so this is the definition. So h theta is equal to that the probability y is equal to 1 given x on parameter theta. Just a second. Hello. হ্যালো কে? ও ধরুন আমি একটু ক্লাসে আছি, আমি রিং ব্যাক করছি। ওকে ওকে, সরি। So the thing is that h theta x is basically that is equal to that is probability. What is the probability that probability for y, probability of y is equal to 1. What is the probability that y is equal to 1 given x on the setting parametric setting theta? So this is the basically this thing, probability that y is equal to 1 given x parametric by theta. So this is the basic understanding of this is theta x on a logical logistic regression setting. Okay, so now you can say that these two things, y is equal to 0 given x theta, y is equal to 1. So this is the, since it's a linear is a binary classifier, definitely these two probability will be 1. So you know that both probability of 0, probability of 1, if it's a binary classifier, it's definitely is 1. So you can say, you can write p of y is equal to 0 theta x theta is 1 minus of this theta. That is very easy to understand. Okay, so this is the hypothesis representation of the logistic division. Now it is another important thing, what is called decision boundary. Okay, so what we see here, what is the logistic regression? Now this theta transpose theta x is basically theta h theta x is basically a sigmoid over this theta transpose x, where this g theta is basically what is g, 1 by 1 plus e to the power minus z. So this is the logistic regression in a nutshell. So now suppose we have to predict y is equal to 1. Okay, if that, suppose we have to y is equal to, if h theta x greater than is equal to 0.5. So this h theta x, if it is 0.5, we can say y is equal to 1. Okay, we have to predict this. So is theta transpose if this theta is greater than is equal to 5. So y is equal to if I that what does this mean? This theta transpose x is greater than 0.5 is definitely we have to, because what is your sigmoids say that if you have to get, you have to say that this this particular thing is greater than 0, then only this part you can see theta transpose, this is the z axis, that means it's theta transpose t axis. Okay, this is z. Now the thing, if theta transpose is greater than in this side, okay, so definitely this is theta x, because this is h theta, it will go over 2.5, is greater than is equal to 0.5, so some here in this position. Okay, so that just for example, if this is, then you can say that it is going there. And predict y is equal to 0, why it is 0 if it is less than 0.5. So this portion we are saying, if this portion, then it is become in this position, you can say it is coming in this position. So this theta, this, then if it is, when it is that theta transpose tx is less than 0, you see that if it is so less than 0.5, it is coming less than that. So this is the thing. So that is the implications of this. Okay. So this g of g greater than is equal to, for when z is equal to greater than is equal to z is theta transpose tx, and this is also theta transpose tx. So this particular a, this is also theta transpose g of theta transpose. Okay, this is theta transpose. So now the thing is that, so, and so what we can say is theta x is equal to g of theta transpose is greater than is equal to 0 whenever this theta transpose is greater than 0. That is exactly what in this, that it we will, this is theta x, this is h theta x actually, so that is going to, this is h theta x. So h theta is equal to, that means g of theta transpose x. So this theta transpose is greater than 0.5 here, then it is, if this theta transpose x is in this theta transpose is greater than in this side. If it is less than this it is in this side. That's all. Now here you can see this what is decision boundary kind of thing, that if you say that we take, just for example, h theta x is a function is this theta 0, theta 1 x1 plus theta 2 x2 as it is written here. Now theta is what? Theta you can say, and theta is basically given by this function minus 3 1 1, and x1 x2 is equal to, so minus 3 1 1 this. If theta is this, means then the equation is basically x1 x2 is minus 3 is equal to 0, and that means that is 0 x1 plus x2 is equal to 3. So this is the function, this is minus 3. Okay, so now what we have to, going to predict on, why, when it's predict y is equal to 1, if this theta transpose x, okay, is greater than is equal to 0. So this is theta transpose x, this theta transpose is greater than is equal to 0. So if it is 1, that means 0. And so this, if it is this, these things means this, then is x plus x2 is greater than is equal to 3. And when it is theta, it is theta x, g theta x minus 0.5, and it is less than is equal to 0. That means when x plus 1. Okay. But now if I say that if h theta x is 0.5, so what is the value? So now if this particular thing, then this is the value x plus 1. If we plot this, we can say this is x1, this is x2, and this is the x plus 1, 3. So this is your decision boundary that will separately count these two, these point clouds. Okay. Now this particular separator, that it is greater than 0 when it is the transpose greater than 0. It's less than 0 when it is the less than the transpose x. It is less than 0. And when this line is called the linear separator or a linear decision boundary. That separator will lead these two point clouds or these points or these two classes. Okay. One very important thing that is very clear, it's very easy to understand from this. But this decision boundary is a property of hypothesis function. So this hypothesis function, this property will give you a decision boundary, not the data set. Data set may be anything. So we cannot say ये data set ये आप use कर लिया तो एक ऐसा decision boundary हो गया. So it basically the what hypothesis function, you can take this is a hypothesis function, you can take this hypothesis function. So this is depends on the hypothesis, not on the data set. The only thing is that the virtue of the or kind of role of this hypothesis function is to properly clearly separate out these star and these dots. That is the thing. Okay, so decision boundary is basically a property of hypothesis function, not the data set. Okay, so I stop here today. So we'll carry on this discussion in the next class. Thank you very much.
So for finding theta, we would be using that algorithm which we learned in the last class and this starting of this class.
Yeah, definitely.
All right.